Okay, guys, let's discuss some hot topics, and then we'll finally can go to have some food. Okay, so let us briefly discuss the most important questions from the list we have now. So there is a microphone over there, and I suppose that you can just take it and random order, and you can just look at any part of the room. Okay, let us start. So, which topics are currently flying under the radar and will become relevant in the next years? What do you think? Which topics are currently flying under the radar and will become relevant in the next years?
Causality.
Bayesian deep learning.
Causal deep reinforcement learning.
Maybe some combination? What do you think? Maybe some combination? Combination.
So, definitely, machine learning is like super dominant these days, and the entire artificial intelligence is being driven by machine learning, but there are definitely things in terms of representations, using complex representations, interpretability, for instance, explainability, and these are things that are becoming more and more important because the range of applications of machine learning is increasing. And in many areas like medical applications, there's definitely a need for explaining things and being able to interpret the way a system gives a prediction. So this is something that is definitely crucial.
Oh, I didn't answer. So if you look in the sciences, you'll see that basically all the sciences are being mostly replaced with a bunch of convnets and things like that. So from that, you can extrapolate that what happens is that vision and a bunch of core machine learning community. Wait, we're not on. This is not on stream, right? This is not recorded.
No.
Okay. So from this,
I'm not recording.
From this, you can extrapolate that what happens is core machine learning fields come up with something, and then about 2-3 years is the delay. So logical thing to do is take something that's happening now very hot in machine learning and see the 2-3 year delay. And so the most natural guess for that is a bunch of reinforcement learning techniques are going to start appearing in a lot of sciences.
I can give a more serious answer, which is that one thing I noticed just at Uber that is being used a lot by Zubin's group and is perhaps less present in machine learning in conferences is genetic algorithms for optimizing stuff. So that's like a deeply unfashionable thing in machine learning, and yet at Uber they're using it a lot. So that's a curious thing that you might think about.
Yeah, so I think that's, you can extrapolate various technical topics, but I think one thing that is maybe under the radar in many machine learning courses, it's curricula at universities and maybe summer schools like these, is the ethical component. So I think now that machine learning has matured and enters many, many different practical applications, we'll talk a lot more about that and take that much more seriously.
Okay, thank you very much. And is there any advice that you wish you were given when you were a PhD student? So maybe you have some advice from your past experience to the current PhD students.
Don't do hedging, in the sense, don't invest all of your money on a single topic, but possibly work on maybe 2 topics related but not necessarily the same, and possibly with different people. Don't trust your advisor 100%. He makes mistakes, especially if it's over 50, And so be always take what he says with a grain of salt, and listen to different people.
Do good research, regardless of whether the paper gets accepted at NIPS or not. I can say that lots of really good papers have never been accepted to any conference. So a lot of very famous papers that you probably have seen or heard of never got any stamp of approval by NIPS, and a lot of times it's because reviewers either don't appreciate or don't really understand ideas which are beyond the stuff that they've seen before. Often the easier papers get into NIPS and not the more interesting ones, but that is a bit opposite to the thing that you should strive to do. The easier papers are not necessarily better research.
Just anecdotally to add to that, there has been research on Nobel Prize winning papers, and there have been papers around that won a Nobel Prize, but they were rejected the first 15 times they were submitted, or something like that.
Never from NIPS.
No, not from NIPS.
I can actually say, so the stuff that I showed in the morning, that was stuff that was actually rejected from NIPS initially. And I think now it's the it was actually rejected for NIPS initially, and I think now it's the 9th most cited paper at ICML for the last 5 years.
Oh, I'll just say, believe in yourself and have fun.
So probably the advice which I would have benefited from most when I started doing research as a PhD student, I had this idea that if I wrote a really, really beautiful proof in appendixes B through F, that the reviewer would care very much about that and would appreciate that over the fact that I hadn't finished writing the abstract and introduction. So basically, a reviewer really wants to know, why should they care? What is new in what you've done, and why should I care about that? And when you're writing a paper, you should make a lot of effort to express that, so the reviewer knows what you've done and why they should care. Why is it new? Why should I care? And if you can't answer that question, then you might also think about whether the project you're doing is useful or not. Because if you don't know, even for yourself, when you come to write, what it is that you're doing that's new, and why should you care, then why would the reviewer? So, it's a lot of fun to spend a lot of time on proofs, and that's what we would rather be doing. But unfortunately, that's not, I think, as helpful in presenting research to anyone but yourself.
That's a good point. So make it very clear that you have an idea for what question you're answering and why you're answering that question.
So since we're doing follow-up, so I said believe in yourself and have fun. So I have 2 students, and one of them is we have role reversal. He advises me more than I advise him, and we spend most of our time finding shorter proofs of things we already know, because that's what makes us happy.
Okay, and if Bayesian neural networks are cool, why they are not so popular, for example, in competitions like Kaggle? Bayesian neural networks.
Because often the simplest solution often works very well. So a lot of this, I can actually give real-world example. A lot of the stuff that we do, we have some joint works with the guys at NASA, working machine learning for space applications. And if you want to solve a task, you start from what is the simplest solution to solve a task, and then can you find better? Okay, if you have an application that you want to solve, then you start from what is the metric of success that I need to actually quantify if I'm doing well or not. You're going to build a bunch of baselines, just simple tasks, simple machine learning models, or not even machine learning models, simple approaches, the current way that people do that. See how well it performs according to the metric of success. Build some simple machine learning models, decision trees, random forests, SVMs, see how well they perform. Just do an ensemble combinations of these, see how well they perform. And then you can try to do some more fancy stuff like deep learning if it makes sense, and see if you can actually get any better results. A lot of the cases, simple approaches work very well, and there's no, it's really silly trying to force deep learning or Bayesian deep learning or anything on cases where you can just have a simple solution that works well. In certain cases, it does make sense if you have high dimensionality for input data, if you need to get a confidence bounds for your predictions, in which case often we see that these techniques, or if you have perception component, then image data, for example, then often these sort of techniques would end up working better.
Okay, any other opinions? Any other opinions on this question?
Having good data and good features is always better than having a fancy algorithm. So design your features well, use like expert knowledge, and use linear regression, and you'll be fine most of the time. It's not recorded.
So one of the things he was saying was you can use, you know, maybe the simplest tool, and I think the specific question was Bayesian deep learning for Kaggle. So, you know, Kaggle, you're just making, your goal actually is a point estimate. You're being evaluated on point estimates. But, you know, if you're doing medical predictions, you want to have confidence intervals, that's a great place to use Bayesian deep learning.
Which basically goes back to metric of success. If you define, okay, I want to get best test accuracy, then you don't really need uncertainty in these cases. You're just going to use a huge bootstrap of lots of different things and just average all of them together. If you want to deploy your things in the real world, then you're going to have a different metric of how well you're doing or not.
Okay. And where do you see the biggest problems, shortcomings in current state-of-the-art machine learning techniques? Yeah, but you already told that everybody is using convolutional neural networks, so maybe you would like to discuss this in more general way.
So I think one really fun thing that goes back to what I was talking about was not just the notion of adversarial examples, but more generally just distributional shift. You can view adversarial examples as competing with a different target than you were trained on. And I actually I don't do research on adversarial examples, but whenever I hear about some machine learning task, I always think, what is the adversarial example version of this problem? And since we aren't recorded, my favorite version of this is imagine the dystopian future when all dating websites use deep networks, and then somebody figures out adversarial example profile for that.
I admit to nothing. Okay, so yeah, so one interesting example, I think, to build on what you've been saying, is that Ben Recht actually recently reconstructed the CIFAR dataset. So he did exactly what they said they did. He built a new CIFAR dataset, and you know, he used his state-of-the-art algorithms that were getting 99.999% on CIFAR on his new CIFAR dataset, and the performance dropped by a lot, like by so much that, you know, the very top running algorithm would, you know, lose 20% of its performance. So that sort of tells you something about, you know, better than human performance on CIFAR. It's not better than human performance on recognizing images. It's better than human performance on a data set that you've engineered your algorithm to solve by, you know, lucky random seeds and, like, you know, querying your test set and, you know, optimizing year after year. So a question might be, actually, how can we do machine learning to solve the problem that we believe we're solving, rather than just chasing benchmarks on a small number of data sets, which is what seems to be a little bit happening.
Okay, very interesting comments, but what drove you to academia? Why you are here? What drove you to academia? Why are you here? Not exactly here, but in general.
My views on academia, I mean, in relation with machine learning, academia, and like that. I mean, it's a very tough moment because unless Google starts a university, I think Yandex already started some kind of.
In some sense.
Yeah, that's probably the way out, because instead of hiring, you know, our students, they directly hire us, and we get maybe a better salary, and the loop is closed at this point. And yeah, it's being in academia and doing machine learning is difficult because companies know the problems, have the data, and pay our students more. So we are in a bit of a hard position, it's kind of it's not easy to figure out incentives towards companies in order to disrupt this vicious circle. There are definitely there are certain initiatives like ELLIS, which is this European network on machine learning researchers that is trying to come to terms with company on a more leveled playground. I don't know whether this will work out, but yeah, the problem is that academia now is suffering because of the success of the field, and it's very hard to recruit and keep good students.
So I'm gonna. So okay. So, over the past many years, 10 years, I don't know, I spent time in industry. I spent time in academia. I must say that the best time of my life that I spent was actually doing what a lot of you guys are doing over here, doing my PhD. Because you're basically your own boss. You basically decide what you want to work on, how difficult you want it to be. If you're challenged, you can switch to a different problem, which is more challenging. If you think this is not interesting enough, then just do something else. I actually see that as like, that is basically what I'm trying to do now. I'm basically trying to give my own students the opportunity to do what I had during my PhD, which is I tell them, okay, tell me what you want to work on, which is actually very difficult, especially like if you're just starting a PhD now, and if you move from a different field, if you move from industry, it can be quite challenging to find interesting problems that you want to work on, interesting problems that developing your own ideas for what you think you would want to do next. And maybe that is something that you should pay attention to as well, which is, I think that is going to be a big thing that you can take out of your PhD as a skill, which is identifying interesting stuff to work on and being able to work on these things independently, being able to develop these ideas, develop your own line of thought, your own arguments about what, like your own position about a lot of these things that we talked about today. A lot of the stuff that we talked about, you might end up disagreeing with in a few years' time, for example. So this is an opportunity for you to try to develop your own ideas.
Yeah, so why am I still in academia? So still, yes, I am still in academia. Well, I started out in academia, of course. We all start out in academia with a PhD. But one of the things I really like about academia is still the academic freedom that you have there. So basically, you can work on whatever you want to work on. Maybe the situation right now is the same in companies, or in some companies at least, for some people. But who knows how it will be in 5 years from now. So this is one of the reasons why personally I still like to be in academia, even though indeed, as you said, we're in hard times now. Student numbers are exploding and going through the roof, but the staff isn't scaling along. So on the short term, we really have a problem. But I think on the long term, the field will just benefit from all this, as long as enough people stay in academia, because otherwise, who is there to teach the new students?
So I can sort of tell you at least a complaint from people who do work at Google or DeepMind or Facebook and so on about what they miss about academia, which is the opportunity to work with students. So they often will have like an intern for 3 months in summer. And the 3-month summer intern is not enough to do a serious, deep project, right? It's enough to like write a little demo and that's it, and maybe get a paper. So, you know, one of the, I think, really great things about academia is that you get to sort of collaborate with people on long-term projects where, you know, everyone sort of brings their own perspective. So sort of I hopefully bring some measure of wisdom and like large sort of horizons. And but what I don't bring is any sort of skill at making stuff run on a computer. And so, like, I think having that sort of complementary thing and having sort of an interaction with other people to like progress on a project is something we have in academia. I think in industry, like, you're much more on your own. You're just doing your thing. Maybe you get an intern, maybe you have like a couple of research engineers, but you don't get like an academic collaboration that runs over a period of time to do like a really deep and ambitious project, which is what we have, I think.
So I'll give answers to two versions of the question. One, why did I go into research? Curiosity, that's it. And then the other thing is about the academia versus industry question. I agree with everything everyone else said, and I'll just add that all of that given, the logical thing to do when any of you are in the position to decide, for instance, when you're graduating or, you know, graduating undergrad, graduating grad, or whatever, postdoc, is to apply on both sides and have a very clear-eyed perspective on both, get opinions from everybody.
Thank you. And all of us see exponential increase in number of papers and visitors of all those big conferences, and because of that, the reviewing process is very, you know, complex, not very well organized. There are a lot of cracks and flaws. What do you think all about this, and how this can be improved?
So I actually consider this to be a major problem because at this point there are over 50 papers per day. That's the lower bound at this point on arXiv relevant to us. Nobody is reading all of them, and personally I actually would really like to. And I think the fact that there are so many papers and so many overlapping papers is actually contributing a lot to the toxicity and aggression of the community. And personally, I think this system is only going to get worse. I don't think there's a sociological solution. I don't think we can just ask people to be nice and pat their competitors on the back. I actually personally want, and I dream that we could make a technological solution to the problem. And I'll just make one comment about what a technological solution could look like. If you look at the open source community, they have a beautiful system now, which is GitHub. You know, people do pull requests. And how nice would it be if one of you finds a bug in one of my papers, and instead of, you know, writing some paper and telling all your friends how dumb I am, you just made a pull request, you know, fix the Cauchy Schwarz, or like, you know, add the 2 that I forgot, or one of these things. You know, or for instance, another thing people get really angry about is somebody didn't cite somebody else. Pull request, add your citation, who cares, you know? So I would like a technological solution to this problem.
That is actually a very good point. So if you find mistakes in someone else's paper or missing citation, just email them and ask them to fix that, which I think is the easiest way to do that.
Okay, I have some personal question. How do you evaluate, and what are you looking for in someone when they apply to you as a postdoc? How do you evaluate, and what are you looking for in someone when they apply to you as a postdoc? I guess maybe some participants would like to do it, so they are asking beforehand.
So it's super hard recruiting students, because if you think of how much Google spends when they have to recruit a person, they spend really literally hundreds of thousands of dollars, and they have a huge experience. They have, you know, you are interviewed by many people. We are absolutely amateurs at doing professional interviews. We as university professors, so it's basically we count on instinct, luck, and we ask, of course, we ask recommendations, because that's, I mean, for us, it's a super big loss that if we get someone who doesn't, who, let's say, is not a good fit with us, because still it's a commitment. We cannot just fire him or fire her, and but it becomes a huge loss of time for us and for the person. So you know, if I was rational, I would try to maximize precision and minimize recall because the loss of a false positive is super high. And, but I really, I mean, it's something I noticed I'm not getting better at because expectations are changing and topics are changing and people are also have different ways of interacting. So it's I expect, I don't know exactly what are my expectations. Definitely if the guy has a paper and has papers published in conferences, good letter of recommendation, and I read these papers, I like them, that's fine. But more junior people are very, very hard to judge. Because we are not very good at that.
So one thing I would like to say here is that I typically don't count the number of papers on your publication list. So I prefer one good original paper about over 10 marginal improvements. So this somehow relates with the previous question, like the amount of papers being published. So maybe another solution, that technological solution like you were proposing, is maybe we should introduce a quotum. Everybody is allowed to write just a single paper every year at most, something like that. And then you have to choose what is your best paper to write that year, and maybe that will help.
So for postdocs, I mean, there's sort of two different answers that I give. So one answer is that, like, I think of the postdocs I've had, some of the most successful have been those whose PhDs I reviewed. So because then you get to know somebody's work pretty exhaustively. And they also then, like, get really stressed about their PhD exam because they know that their job is on the line, so they do a good job. But yeah, so Dougal Sutherland, who's a postdoc of mine who just got a position in Canada at UBC, so he was a student whose PhD I reviewed. And on the strength of that review, I said, like, I would love you to come and work with me as a postdoc. So that's one thing. And I think related to that is that, like, for postdocs, ideally, I want someone who can teach me something I don't know. And so when I look at the, I guess, portfolio of work that they do, I look for something where I would like to learn about a problem and they know about it and I don't. And then if they can explain it to me and I can understand them, then that is really productive. So recently, one of my current postdocs knows a lot about survival analysis. I'm really interested in testing when, like, you know, maybe half of my people that I'm testing die in the middle of it, because that's what happens in medicine. So, you know, that's something I wanted to learn about. She knew about it, so then I made her an offer.
Also, I would suggest publishing in workshops, suggested to, like, related to the topic in which you want to specialize. So, in my case at least, like, when I get many postdoc applications and, like, I just go quickly over the CV to see if there's any venues I recognize. Like, you look for NAIPS or ICML, but these are very stochastic by now. It's very difficult. You can have good paper, I mentioned before, and good paper that gets rejected. Workshops usually would be a very different mechanism, where workshops' idea is to discuss and share ideas. And usually you have higher chances of getting into a workshop, and the point is that for you to go there and discuss your ideas with others. And a lot of the cases, you would just end up, like, discovering really people that you want to work with just for these workshops, because I would go to these certain workshops in topics that I find interesting, and just talking to others in these venues.
Okay, more technological question. And can you give us any really industrial use cases when generative models like GANs were applied successfully? Can you give us use cases when modern generative methods, generative models like GANs were successfully applied?
For image data or for any data?
just for any data?
Well, in NLP, you use it a lot, and like machine translation uses conditional generative text, for example. That is basically machine translation. In image data, it is a bit more difficult to justify, but use it a lot in content consumption. I think Twitch used GANs to do super resolution. So like to give you, like you send low resolution images and then you do super resolution on the edge device to make it look more nicer for the user. It's more difficult to justify these sort of things in scientific applications, but there are cases where people use these for data augmentation, but you need to be very careful in that case.
Okay. And today actually we discussed many similarity metrics like MMD, KL divergence, Wasserstein metric. Is there anyone that is clearly superior, or does this depend a lot on the application?
Depends on the application.
So yeah, like it's sort of hard to say in statistical testing that one method provably always dominates another. There are instances where that's true. So like you can sort of show that chi-squared distances always provably are uniformly more powerful than an L2 distance for testing. So that's a classic result. But yeah, like in other cases, it really depends on what you want to do. There's, in terms of sort of mass transport, Léon Boutou has a very nice paper where he's sort of comparing different distances, and he's showing that, one Wasserstein has geodesics, so mass transport paths, which are better than MMD. So MMD, in this case, has, I think, much less desirable transport paths than Wasserstein does. So, depending on what you want to do, you should use the right tool for the job. But I can't just say like always use KL. I mean, apart from anything else, you probably can't estimate KL, and if you think you are, you're probably not. But use what works. Yeah.
I see. And can you tell us what mistakes do your PhD students usually do, and how to avoid them? And would you redo your own PhD if you will be able to do it?
Oh, this one's really easy. My PhD students are way better than me. So I'm the one making all the mistakes.
I think it's really back to something I said earlier, that like people really want to concentrate on like, formatting the figures in their experiment section, or like fixing that proof in Appendix C, or, tightening some rate. And no one wants to sort of like explain what they've done clearly in the first part of the paper. Unfortunately, that like understanding why you're doing what you're doing is like really, really important, even though it's a mental strain. Like it's really hard for your mind to sort of move in that direction and away from the fun part of like writing up code and stuff. So that's something I find I have to lean on my students to do. Like they really don't want to do it, but they really need to do it.
It's basically the same point from a different perspective. So I noticed that with a few students, actually I noticed that like many times, where before you write any code, make sure that you understand what the code should be doing, what you expect experiment outcome should be. If you don't see that experiment outcome, what does it mean? Basically understand what you're doing before, because otherwise you're going to end up spending a lot of time just coding something quickly. It's fails, you do some random changes, still fails, just like doing a very long greedy search until you get something that works well. Instead of just sitting down and thinking, okay, I'm going to do this experiment design, this is why I'm doing that, this is what I expect to see, this is what it means if I don't see what I get to see. And then you can start analyzing things and make that like compartmentalize that and like use that in smaller blocks until you actually understand why it fails. And often that by itself will highlight interesting new questions to ask and to try to answer.
Yeah, so this is more like a mistake that I made in the past. So, not my PhD students, which is that I used to start thinking from a theoretical perspective. So you're interested in the theory part, and you're thinking on a theoretical level, and then you identify a nice problem to solve. You think, oh, this is interesting, really sounds interesting. You solve it. And then at the end of the day, you get the data set selection problem, where you just have to find this particular data set where you can apply your method on. and then maybe you don't find it, or maybe the data doesn't really satisfy your assumptions, and then you think, oh well, okay, too bad. It was a nice paper. I didn't find any data. Let's move on with the next interesting theoretical problem. You can keep doing this for a while, but what I noticed myself was that when I turn things around, so I start from a data set, and then I just sort of immerse myself into the data. It's much easier to generate new theoretical questions that are actually relevant for this data set. So this is a much more inspiring way of doing research, I found. And this took me a long time to figure out by trial and error, so maybe this is something you can, I can bootstrap you or something like this.
Cool. Yeah, please.
Related to that, I mean, the general idea of how to conduct research, something I learned from my mentors that I was not very good at was I would kind of get caught in ruts. It wasn't just I would frequently get caught in a theoretical rut, but I'd kind of like try to make one analysis work rather than checking, many things. So I was very heavily influenced by a guy named Sham Kakade, what probably many people know about. And whenever he looks at any problem, he just kind of very quickly makes a bunch of dirty solutions. He kind of like in his head sort of makes the map of all possible dirty solutions you can think. What if you use the squared laws? What if you use Cron-Shannon, gradient descent, this, that, pseudo-inverse, use this, try all the different techniques, use Bayesian deep learning, use whatever you want, just try all the things and kind of, think top down from the problem rather than getting caught in the leaves.
Okay. But then, what do you think about machine learning approaches with when some subject domain knowledge is integrated? Nowadays, for example, machine learning with physics-based informed machine learning is quite popular when they try to replicate some physical system. So what do you think about this? Will this be popular, or will this be important for applications?
So I guess one thing that Ben Recht likes to be sarcastic about again, Ben Recht, is like that machine learning is rediscovering control theory from the 1970s, which is another way of saying physics-based machine learning before we add all of the fancy decoration. Again, because this is not recorded, a nice example is that you might have read some headlines about, DeepMind invents an AI to make the cooling work in Google data centers. And actually, the person who told me this was Stephen Boyd, who looked at what they had done and had noticed that they were doing basically some, quite well implemented reinvention of a sort of feedback control system from some classical textbooks, which is, nice to have reinvented, but they could have also read the textbooks. So that's perhaps, physics-based or, shall we say, informed machine learning, I think is a good way to go.
So many successful machine learning applications nowadays, they are that successful because of the availability of large data sets, right? But and data sets are growing and growing, of course, but they're sort of, at some point a few years ago, big data was the real challenge, right? But I think actually an even more difficult challenge is small data. So for example, in medical applications, which is a very important domain, there's really not that much data available. You can't just clone patients and do whatever you want with them to get the data. So in those type of applications and in many other fields as well, I think for the next 50 years or so, we will keep combining expert and domain knowledge with machine learning methods.
They're not being recorded, right? So there are other things like, quantum computing is something that is being, advertised at least, and it's not clear what are the real progresses, but it's definitely, there are huge investments and there are progresses that are being made. So this is, it's definitely interesting to think about quantum implementation of learning or ways of doing machine learning at quantum level. There are papers that are being written on that, but this is something that's possibly will become interesting in the future because of the possibility of overcoming computational bottlenecks through quantum computing. So this is, I find it super interesting. I hope I will live long enough to see something cool, at least that I can buy or or get to use.
Okay, then I have the following question. It's well known that nowadays there are big companies like Google DeepMind and others who invest a lot. First of all, they invest in reinforcement learning because they believe that reinforcement learning will be useful for something. Although nobody see at least now good applications. So, do you think one day there will be some application of reinforcement learning to some real industrial problems? Because although it's very difficult due to all these things related to domain shifts and differences between distributions during testing and training. And the second question is, what do you think finally will DeepMind earn a lot of money? Because, well, according to recent reports, they just are losing money and not earning them. Maybe that tale with a cool AI lab inside Google soon will end.
So reinforcement learning is the ultimate learning problem, right? I mean, it's hard to get any more general than that. You can have POM-DPs or things like that, but I think any application in which you have interaction, or like for instance human and machine interaction, you have to use some reinforcement learning, because there is a notion of state, there is a notion of uncertainty, there is a notion of partial observability, there is a notion of delay, and all these things are only modeled through reinforcement learning. So I think most future applications of AI, where AI will be sort of living in between, among humans and interacting with humans, will have to depend on reinforcement learning. So I subscribe that kind of investment, and I wouldn't care if it's in the short term. I mean, Google has no cash problem, I believe. So I think it's a very wise way of investing this money, as opposed to trying to extend human life or things like that. And in self-driving cars. I mean, how can you do self-driving cars without serious reinforcement learning?
So, first comment about there are ways of doing human in the loop without reinforcement learning, but just talking about specifically reinforcement learning. One of the things I tell my students is that if they insist on doing reinforcement learning, think very hard what you want to do in the field, because it's swamped. There's huge amount of people just doing lots of derivative research, and it's very, very difficult to find interesting stuff to do. In my mind, one of the most interesting things, if you want to do reinforcement learning, would be to work on model-based reinforcement learning rather than model-free. And be very careful about how you evaluate whether you're actually making progress in the field or not. One of the biggest issues that we have in reinforcement learning is that people do 2-3 repetitions for the experiment, and there's been some reproducibility studies showing that by just doing more repetitions, you can show complete opposite results from what was published. A field is very noisy. Model-free reinforcement learning specifically is very difficult to understand even what should be a starting point, what you should use as a model to build on, because I don't know what is the current what is actually the current good starting point, because it's just it could be because of noise that they got slightly better results than someone else. In model-based, it's slightly different because we often look at different tasks. For example, we would look at control tasks. You have a gripper, then you want to look at, did you manage to reach the object or not? A pendulum swing up, which is the most simple control task you can imagine, which is just you want to swing up pendulum and balance it. More complicated ones as well, but in that case, one way of evaluating if you're doing well or not is, did you solve the task, yes or no? And then you can look at the frequency out of like many repetitions, how many times you actually solve the task. 90% of the times you manage to solve the task. And I think that actually ends up giving us much more stronger signal about whether we actually make progress, we actually manage to improve stuff on existing literature, or whether we're just going back and forth in cycles.
Okay, and the last question of today's panel, yeah, the last one. So, are there any problems for which we shouldn't apply machine learning due to ethical reasons?
I would also say that model-based reinforcement learning is very challenging because building a model of the world is very difficult. And if anything, like the most difficult question in my mind in reinforcement learning is learning good state space representation, which is tied very closely to learning good models of the world and learning how the world will behave next time. Basically building prediction models or dynamics models of how the world will evolve over time.
Well, I personally wouldn't work on military applications, but there's a lot of discussion nowadays also on, say, fairness, and for example, all kinds of decision making. Is it fair, yes or no? But if you read the newspapers and the discussion on that level, I think one of the things that people often forget is that how do you know whether a human decision making is fair? So actually one of the advantages of algorithms over humans is that you can understand an algorithm, but can you ever understand a human? So can you look inside the box whether somebody is transparent and fair? So I don't think that fairness that we should not do or we should not continue working on general decision making even when fairness may be at stake. But of course we should look closely into it, into this aspect. But some people would say, well, just don't apply your data-driven algorithm because it's not fair or whatever, or we see that it's not fair, but then if we just go back to human decision-making, then how do we know whether that's fair?
So machine learning, of course, I mean, it's a dual technology in the sense you can apply it to good purposes and bad purposes. It's like if you study at foundational level, you study reinforcement algorithms for reinforcement learning, that's okay. Of course, this algorithm can be applied to bad things like chasing people with a drone, but it's the foundational study is not bad per se, and conferences like NeurIPS do not take papers that have explicit military applications or applications that relate to in an apparent way to harming human beings or stuff like that. And I agree with that. I mean, there are specialized conferences for that that work on these topics. I don't think that as scientists we should work or advertise or participate in conferences that have military applications or of this kind of. Whereas I wouldn't put any boundary to the foundational research, of course. This should be completely free. I mean, you never know. I mean, it's impossible to predict.
So I'll say that I'm worried about machine learning, but I'm actually more worried about all technology in general. And I urge everybody to keep their eyes open for ethical problems. And I want to tell everybody how scary this situation is. I want to put fear into everybody's hearts for the rest of their lives. So everybody in the world, at every level of power, as high up as you want them to get, as low as you want them to get, they have one of these in their pockets. Okay, let me tell you about this device. This is not your device. Nobody in this room owns this device. The companies that own these devices can remote delete whatever they want from these devices. You do not own this device. Now let me tell you why to be frightened. In a couple of years, a bunch of your friends are going to get brain chips, okay? You're going to have to get a brain chip because you're going to be Googling things 100 times slower than everybody else. So you're going to have to compete. You're going to have to get a brain chip. Guess who's going to make the software for your brain chips? The same people that can remote delete things from your phones. So you're going to have remote deletion in your brain in a couple of years. So good luck in the future.
maybe there's some things you don't want to remember anyway. So yeah. So I guess one talk that I really enjoyed recently, which I advise you all to watch because it's online. So Timnit Gebru gave a talk recently at the Machine Learning Summer School in London about the ethics of data, and it's a beautiful talk. And I'm not going to do it justice because she's way more articulate than I am. So I encourage you to watch it. But where she sort of started with this talk, like she talked about her PhD, and in her PhD, she was using Google Street View images to predict basically like incomes in neighborhoods. And that's fine, and she got the project done and it worked. But what then occurred to her is she was using Amazon Mechanical Turk to label these images. And then thinking about that, what that means is that you're paying people in India like, 5 cents an hour to do the data labeling work that you then get your PhD so you can earn like 200,000 a year at Google for. So like that's a little bit troubling. And if we think about the utilities we use like Facebook and Google and so on, like somebody, a human, is going through and labeling absolutely horrific images so that we don't have to see them. And they're getting paid virtually nothing to do that. So, is this ethical? Like, who is labeling our data for our machine learning algorithms? The people who are doing that, I mean, these are in perhaps some of the worst labor conditions today, are being paid very little to do like a really terrible job. And this is only going to increase because, as we get more and more data hungry machine learning algorithms, we're going to rely on huger and huger populations of people basically like laboring in these sorts of conditions. Like these are the modern sweatshops to basically like generate the data for our algorithms so that we don't have to see unsavory things on our friends' feed on Facebook. So, yeah. Only fair trade data, exactly. Like, all my data's been free trade. And so.
Okay, guys, it was a long day. So, guys, let's thank the speakers for this wonderful discussion.